Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again after months of spouting gibberish.
We meet the NASA scientists who repaired a spacecraft from 15 billion miles away. The Voyager 1 is known for being the first spacecraft to go beyond our solar system. So when it stopped sending data back to Earth last November.
Ever wondered what secrets lie at the very edge of our solar system? After decades in deep space, Voyager has reached the mysterious edge of our solar system, and what it's detected is sending shockwaves through the space community. From puzzling signals to bizarre cosmic forces, Voyager's discoveries are challenging everything we thought we knew about the final frontier. What secrets lie beyond the edge, and how could they reshape our understanding of the universe? Buckle up for a journey that will leave you questioning the very limits of space as we know it. NASA's Voyager mission has captivated the imagination of scientists and space enthusiasts alike, providing a window into the far reaches of our solar system and beyond. As it journeys through interstellar space, Voyager has delivered unprecedented discoveries and data that have stunned even NASA scientists. From detecting unexpected plasma waves to offering new insights into cosmic radiation, the Voyager probes have exceeded all expectations, continuing to perform their mission over 40 years after their launch. Launched in 1977, the Voyager mission consists of two twin spacecraft, Voyager 1 and Voyager 2, designed to explore the outer planets of our solar system and eventually enter interstellar space. Originally intended to perform a grand tour of the outer planets, both probes exceeded their initial goals by journeying past their intended paths and continuing on an interstellar trajectory. Voyager 1 is the farthest human-made object from Earth, while Voyager 2 took a unique trajectory that allowed it to encounter Uranus and Neptune. Both probes carry messages for potential extraterrestrial intelligence, known as the Golden Records, 12-inch gold-plated phonograph records containing sounds and images representing life on Earth, alongside greetings in 55 languages. These records serve as time capsules, holding snapshots of life on Earth for any intelligent civilization that may eventually encounter them. In 2012, Voyager 1 shocked NASA and the scientific community when it became the first spacecraft to enter interstellar space, followed by Voyager 2 in 2018. Both probes detected unexpected changes in plasma density at the heliopause boundary, showing that this area was far more dynamic than anticipated. Since entering interstellar space, Voyager 1 has encountered plasma waves, mysterious ripples in interstellar plasma caused by solar outbursts. These waves reveal the density of the interstellar medium, helping scientists understand its composition. Another significant discovery was an unexpected, unexplained pressure at the edge of the solar system. This phenomenon could result from an interaction between galactic cosmic rays, interstellar plasma, and magnetic fields, but the exact cause remains unknown. This pressure suggests that the environment at the solar system's edge is more complex and turbulent than previously believed. As of now, both Voyager 1 and Voyager 2 have crossed into interstellar space, the region outside the heliosphere where solar wind particles no longer dominate. This boundary, known as the heliopause, is where the solar wind's influence wanes, allowing interstellar particles and cosmic rays to increase significantly. Voyager 1 is currently over 14 billion miles from Earth, and Voyager 2 follows at approximately 12 billion miles. Despite their vast distance, both probes continue to send data back to Earth, although transmissions can take more than 21 hours one way. The discovery of the heliopause boundary itself was groundbreaking. Voyager's crossing provided the first direct measurements of interstellar space, allowing scientists to understand better the differences between the interstellar medium and the solar bubble surrounding the Sun. Voyager 1 and Voyager 2 have uncovered several bizarre and groundbreaking phenomena throughout their journey, each providing a glimpse into the unknown. From the outer planets to interstellar space, here are some of the most extraordinary discoveries Voyager has made to date. One of the most surprising discoveries came when Voyager 1 crossed the boundary of the heliosphere in 2012, followed by Voyager 2 in 2018. This boundary, known as the heliopause, marks the transition from the region dominated by solar wind to the interstellar medium. scientists were surprised by the complex and dynamic nature of this region. Voyager detected a pressure on the boundary, suggesting a previously unknown force at play. This pressure could stem from cosmic rays, magnetic field interactions, or even a dense wall of hydrogen at the edge of the solar system. The crossing into interstellar space revealed that this boundary is not a static barrier, but rather a turbulent, moving region that expands and contracts with solar activity. After Voyager 1 entered interstellar space, it detected unexpected plasma waves, low-frequency oscillations caused by interactions between cosmic rays and interstellar plasma. These waves, which create eerie sounds when converted to audio, give scientists insights into the density of interstellar space. Voyager's measurements showed that the plasma density in interstellar space is higher than expected, offering clues about the structure and composition of the galactic environment. Scientists expected Voyager to detect a magnetic field in interstellar space aligned with the galaxy's magnetic field. Instead, Voyager 1 discovered that the magnetic field in the interstellar medium was slightly tilted and still influenced by the Sun's magnetic field. This unexpected tilt suggests a complex interaction between the heliosphere and the interstellar environment, hinting that our solar system might be squashed rather than a perfectly spherical bubble. As Voyager approached the heliopause, it detected a cosmic ray boundary layer filled with an unusual mix of solar and galactic cosmic rays. In this region, Voyager encountered a sudden drop in solar particles and a spike in high-energy particles from interstellar space, indicating the mixing of solar and galactic influences. This cosmic ray layer was previously unknown, and its discovery suggested that the Sun's protective influence doesn't simply end, but gradually fades, creating a turbulent boundary where particles mix in complex ways. When Voyager 2 passed by Saturn in 1981, it discovered active geysers on the icy moon Enceladus. These geysers spew water and organic molecules into space, hinting at the possibility of a subsurface ocean beneath Enceladus's icy crust. This finding has profound implications for astrobiology, as it suggests that Enceladus might be capable of supporting microbial life. Additionally, Voyager provided close-up views of Saturn's rings, revealing braided and twisted patterns caused by gravitational interactions with Saturn's moons. Voyager 2, the only probe to have visited Uranus and Neptune, revealed some of the most bizarre weather patterns in the solar system. One hypothesis based on Voyager's data is that methane deep within the atmospheres of Uranus and Neptune could undergo extreme pressure and temperature conditions, breaking down and forming diamonds that rain through the interior of these icy giants. This exotic phenomenon of diamond rain remains speculative, but it is one of the leading explanations for the unexpected atmospheric behaviors Voyager observed. Voyager 2's encounter with Neptune in 1989 uncovered a massive storm system known as the Great Dark Spot, similar to Jupiter's Great Red Spot. This storm, nearly the size of Earth, exhibited winds exceeding 1,500 miles per hour, the strongest observed in the solar system. The spot was transient, disappearing when Hubble later observed Neptune, suggesting that Neptune's atmosphere undergoes rapid and extreme weather changes. During its flyby of Jupiter, Voyager discovered intense auroras on the gas giant, caused by interactions between Jupiter's magnetic field and particles from its moon Io. Voyager also captured volcanic eruptions on Io, the first direct observation of active volcanoes on another world. Io's volcanism is driven by intense tidal forces from Jupiter, which create frictional heat in the moon's interior. This finding redefined our understanding of geological activity in the solar system, revealing that moons could be more volcanically active than planets. In 1990, Voyager 1 took its iconic pale blue dot image, capturing Earth as a tiny speck in the vastness of space from 3.7 billion miles away. This image, taken at the request of Carl Sagan, highlighted the fragility and smallness of our planet, evoking a profound sense of humility and perspective on our place in the universe. One of Voyager 1's more recent discoveries has been the detection of a hum in interstellar space. This low-frequency hum is a continuous sound caused by the vibrations of plasma waves in interstellar space. Unlike the occasional plasma wave spikes caused by solar flares, this hum is steady and represents the ambient plasma environment far beyond the heliosphere. This faint music of interstellar space has given scientists a new way to measure the density of interstellar material surrounding our solar system. Can Voyager detect extraterrestrial life? While Voyager was not designed to detect extraterrestrial life directly, it provides data on the environment beyond our solar system, including measurements of cosmic rays, magnetic fields, and plasma waves that could potentially influence any alien biology if it exists. Indirectly, the data it sends back could help scientists understand the conditions that might support life in other star systems. The golden record, however, is Voyager's only message aimed at intelligent life forms, containing information about Earth and its inhabitants. If an advanced extraterrestrial civilization were to intercept Voyager, this record would offer them a glimpse of Earth's culture, location, and history. The Voyager spacecraft are equipped with a suite of instruments tailored for studying the outer planets and the interstellar medium. While their power is limited, these instruments have proved invaluable for the groundbreaking observations they continue to make. The main instruments aboard Voyager include Imaging Science System, ISS. Although no longer operational due to the probe's distance from the Sun, the ISS captured breathtaking images of Jupiter, Saturn, Uranus, and Neptune, as well as their moons. Plasma spectrometer, PLS, measures the properties of plasma, hot ionized gas, in space. This instrument was crucial in understanding the solar wind and its interactions with the interstellar medium. Cosmic Ray Subsystem, CRS, detects cosmic rays, high-energy particles from outside our solar system. This data helps scientists understand the galactic radiation environment. Low-energy charged particles, LECP, measures the presence of ions and electrons, giving insights into the heliosphere, the bubble of charged particles surrounding our solar system. Magnetometer, MAG, measures magnetic fields in space, particularly those in the vicinity of the outer planets and in the interstellar medium. Ultraviolet spectrometer, UVS, and photopolarimeter system, PPS. These detect ultraviolet radiation and analyze light polarization, respectively. Due to the decreasing power supply, some instruments have been turned off to conserve energy. However, the remaining active instruments still provide valuable data as Voyager probes the outer reaches of our solar system and beyond. Comparing Voyager with JWST and Hubble Voyager, JWST and Hubble serve different purposes, but all contribute to humanity's understanding of the cosmos. Here's how they compare. Voyager is an interstellar probe, traveling outward into space and providing measurements of the solar system's boundaries and interstellar medium. Hubble orbits the Earth, and JWST orbits the Sun at the L2 Lagrange point, focusing on deep space observations with high-resolution imaging. Hubble and JWST are advanced space telescopes designed to observe distant galaxies, nebulae, and exoplanets in detail. JWST, specifically, uses infrared capabilities to peer into the earliest epochs of the universe, while Hubble captures detailed images in visible and ultraviolet light. Voyager's role, however, is more exploratory and localized, focusing on in-situ measurements of the interstellar environment. JWST and Hubble use state-of-the-art imaging and spectroscopy, while Voyager's instruments were designed primarily for solar system exploration, with less emphasis on imaging and more on magnetic fields, cosmic rays, and plasma interactions. Both Hubble and JWST are expected to operate for decades, but within close proximity to Earth. Voyager, however, has ventured into a region no other probe has reached, creating a legacy of solar and interstellar science that will outlast its power reserves. Will Voyager last for another decade? Voyager's longevity has been remarkable, but its remaining lifespan is limited due to diminishing power. Both Voyager 1 and Voyager 2 are powered by radioisotope thermoelectric generators, RTGs, which convert heat from decaying plutonium-238 into electricity. Each year, the power output decreases by about 4 watts, leading NASA to turn off non-essential systems and some instruments to conserve energy. Based on this gradual power loss, NASA anticipates that the probes may be able to operate until around 2030, though not at full capacity. By 2030, Voyager's power will likely be insufficient to run any of its scientific instruments, meaning the probes will become silent, no longer transmitting data back to Earth. At that point, they'll continue their journey through interstellar space as time capsules, carrying their golden records as messages to any future civilizations that may encounter them. In these remaining years, the Voyagers are still expected to send back valuable data, especially about the interstellar medium, as long as key instruments like the Cosmic Ray Subsystem, CRS, and Plasma Wave Subsystem, PWS, remain operational. Each piece of data they send back brings us closer to understanding the true nature of interstellar space and the conditions beyond the heliosphere. Though they likely won't last another full decade as active instruments of science, Voyager's legacy will endure, and their journey into the cosmos will continue for millennia. During Voyager's journey, did it ever encounter a black hole, or is NASA capable of maneuvering it to avoid one? No, neither Voyager 1 nor Voyager 2 has encountered a black hole in their journeys. The odds of encountering a black hole are exceedingly low, primarily because black holes are relatively small and rare on a galactic scale, and space is vast. The likelihood of a random collision between the Voyager probes and a black hole is almost zero, especially since the probes are traveling on fairly predictable, open trajectories out of our solar system. In terms of maneuverability, NASA has very limited control over Voyager's path. The probes were designed for specific trajectories to take advantage of gravitational assists from planets like Jupiter and Saturn. After these encounters, Voyager's trajectory was set on a fixed course, mostly dictated by the gravitational forces it experienced in the early stages of its journey. Although tiny adjustments to trajectory were possible during their planetary flybys, the probes lack any propulsion systems to significantly alter their paths in deep space. Voyager's navigation through interstellar space isn't actively controlled. NASA can still send limited commands, but these are largely focused on instrument management and do not involve steering. The probes are simply drifting through space, following the direction imparted by their last planetary encounters. Fortunately, this means they'll continue to travel far away from the dense regions of the galaxy, where black holes are more common, reducing any risk of an encounter. And that wraps up our journey with Voyager to the very edge of our solar system. These discoveries remind us how vast and mysterious our universe truly is, and just how much we still have to learn. The data Voyager sends back not only deepens our understanding of space, but also gives us perspective on our tiny place in it. With every mile Voyager drifts further, it carries with it humanity's curiosity and our message to the cosmos. If you enjoyed this look at Voyager's incredible mission, don't forget to like, subscribe, and hit the notification bell so you never miss our next deep dive into the mysteries of space. Thanks for watching, and keep exploring.